Dynamics. And of course, all good dynamics starts with Newton's laws of motion because that's where it all begins. All our calculus and what have you, it all comes from Newton. And his first law, corpus omni preservari. For those who don't do that, and I know we've got a couple that do, but excuse us for while we talk to the ignorant, Okay, that actually means everybody continues in a state of rest or of uniform motion in a right line unless it is compelled to change. And that's what we were basically talking about before, although we talked about acceleration, not forces. If I'm moving, I'm going to stay at a constant velocity unless I have an acceleration in a particular direction, which will either speed me up or slow me down. And that's what this is saying. The body will continue in its state of rest or uniform, so constant velocity, unless it's compelled to change by some force. Okay, so that's the first part of Newton's laws. The second one is the one that most people know and recognise. Newtonium modus proportionalium. Okay, so in other words, the change of motion is proportional to the motive force impressed and is made in the direction of the right line in which the force is impressed, so it's in the direction. Or another way of saying that, motive force is proportional to change in motion. Well, change in motion or change in velocity is acceleration. So force is proportional to acceleration, which means force is equal to some constant times acceleration, and it turns out that is mass times acceleration. Now, it's not just a fluke, that's the way force is set up. The units of newtons is actually defined as kilograms meters per second squared. So the extra unit we're throwing in there is kilograms or mass. So force is always mass times acceleration. The third law, actione contrarium, is probably one of the often misquoted ones. To every action there's always opposed and equal reaction, or the mutual actions of two bodies upon each other are always equal or directed in contrary parts. The way a lot of people just say it is, to every action there's an equal and opposite reaction. Okay, but what it's basically talking about is reaction forces. Like, I'm standing here at the moment. Now, there is a force acting on me at the moment, and that is the force due to gravity. Yet, I'm not moving. I'm able to stand here quite fine. I'm not being pulled through the floor. And that's because there's another force acting in the opposite direction, the force of the floor acting up on me, and they balance each other out, and so I get to stand here without moving. So for every force one way, there's a reaction force the other way. And we'll talk a bit about reaction forces when we look at our four-unit type of motion. So they're basically the three laws. Now, we're interested in acceleration because force is mass times acceleration. Well, mass is, of course, just a constant. So when we talk about force, it's the acceleration that we'll end up doing the calculus on. So the different pieces of acceleration. We have seen already in 2-unit that acceleration is equal to the second derivative of displacement with respect to time, or the first derivative of velocity with respect to time. And in 2-unit, acceleration was always a function of time. More recently, we've seen that, hey, acceleration could also be a function of displacement. And we can use our d dx of a half v squared. That now links velocity and displacement together. There is a third one we sometimes use. Acceleration could also be a function of velocity. Now, depending on the variables, if the link is between, we want to get an equation that links velocity and displacement together, we would use acceleration as v to v dx. The other one, of course, we could use, if it's a link between velocity and time we want to put together, then we could use the v to t and turn it upside down and becomes the t to v, and then we can integrate with respect to v. So it depends on what sort of equation we want to get with velocity as to which one we would use. So here is a very, very old question now, 1981. We're going to assume the Earth is a sphere, radius capital R, you'll notice back in 1981 they didn't worry about numbers. They sort of called things r. And at that point, at a point little r, which is of course greater than capital R from the centre of the Earth, has to be greater than or it'd be inside the Earth, the acceleration due to gravity is proportional to 1 on little r squared and is directed towards the Earth's centre. A body is projected vertically upwards from the surface of the Earth with initial speed capital V. We're going to prove that it will escape the Earth's gravitational pull if and only if velocity is greater than or equal to the square root of 2gr, where g is the magnitude of acceleration due to gravity at the Earth's surface. So, this is the Earth, my blue circle here, the blue planet. Okay? And so this red line, I'm just thinking is the path of the particle. Of course, it'll never go inside the Earth, unless we dig a tunnel, I suppose. What do we know? There's our little particle that wants to escape the Earth. I've just put it in a random position. I know at the Earth's surface, little r is equal to capital R. I know the initial velocity at that point was capital V. I also know the acceleration is negative g at the Earth's surface. I also know that should this particle stop at its maximum height, velocity will equal 0. Now, what we tend to do with these sort of questions is we draw a force diagram so we can get a feel for what's happening. We define the direction which we want to be positive. And that's going to be our overall, or our what we call our resultant force. I've defined up to be positive for this question. So the first thing I do is that. But we're dealing with forces, so I'm saying, well, that force is going to be mass times acceleration. The variable we're using for displacement is r. So for acceleration, I've used r double dot. So mr double dot is the resultant force. I now on this diagram place all the forces that are acting on this particle. Now the force we know is the force due to gravity. And it was said it was the magnitude of acceleration. Oh, it was on the page before, wasn't it? We said it was proportional, the acceleration was proportional to 1 on r squared. Okay, so that means the acceleration is equal to a constant. I've used mu for the constant. But I want a force. Force is mass times acceleration. So I have mass times mu over r squared. That is my force, and it's acting towards the centre of the Earth, so it is going down. There are no other forces in this problem, because to start off with, we're not worrying about air resistance or anything like that. However, Newton's third law, all our forces must balance. So my resultant force will end up being the sum of all the other forces. Okay? So that's how we set our equation up. The resultant force is equal to the sum of all the other forces. Well, the other forces, there is only one. It's m mu on r squared. It's in the opposite direction to which I've defined to be positive. So it's minus m mu on r squared. There is the equation we can start with. In this case, I can divide through by the mass, and I have an acceleration equation in terms of displacements. So acceleration in terms of displacement, I'm going to work out what mu is first of all. I can actually get a value for this constant. We said when little r is equal to capital R, the acceleration was equal to minus g. So I can sub in, and I get actually that my constant is equal to g times capital R squared. Okay. Now whether you do that now or whether you do it later, it doesn't really matter, but we are going to need to find it to solve our problem. So okay, I now have acceleration minus g capital R squared on little r squared. So I'm going to use d dx, or in this case d dr, because we're using r for displacement, of a half v squared. This will allow me to get an expression that links velocity and displacement. Okay, half v squared will be gr squared on little r plus a constant. Remember, g is just a constant, r squared is just a constant. So all I was really integrating was the minus 1 on r squared. Integrate minus 1 on r squared, you get positive 1 on r. Multiply by 2 to get rid of that half. But again, I'm not going to worry about multiplying the little c by 2 because a little constant is a constant. Okay, so some more conditions that we know so I can work out. Something that links displacement and velocity together. And we said that when little r was equal to capital R, little v was equal to capital V. So I can sub that in, and my constant becomes v squared minus 2gr. So I now have an expression for velocity in terms of displacement. Remembering, capital R, capital V, little g, they're all constants. The only variable there is little r. Okay? We're trying to prove the escape velocity. If it escapes, that means the particle will never stop. It'll just keep going, keep going. Because if it stops, then it will come back, so it doesn't escape. So our particle doesn't actually stop, which means displacement, if you like, will approach infinity. It'll never stop. So the limit as r approaches infinity of velocity squared, let's work that out. That will be my velocity that I'll escape at. The limit as r approaches infinity, well, remember r, if I put infinity on the bottom of the fraction, that fraction will become close to 0. I mean, think of your curve, y equals 1 on x. As x approaches infinity, y is approaching 0. So it really is just that simple hyperbola there that we're talking about. It's just we've put funny letters there. So I know the limit of velocity squared will be capital velocity squared, or capital V squared, minus 2gr. Okay? But v squared has to be greater than or equal to 0. I can't change that. So I now know capital V squared minus 2gr will always be greater than or equal to 0. So v squared will always be greater than or equal to 2gr. So what is that saying? In order to escape the Earth's atmosphere, capital V squared must be greater than or equal to. So the minimum of that velocity must be the escape velocity. Because clearly if I go faster than it, I'm still going to escape. I'm interested in the minimum velocity to escape. So that minimum velocity, well, velocity must be greater than or equal to the square root of 2gr for the particle to escape, but the actual escape velocity then would be the square root of 2gr. So that solves our problem. Well, it's one way of solving that problem. All right, it's now asking us to assume that indeed we are travelling with that escape velocity, the square root of 2gr. We're going to prove the time it takes to rise to a height of r above the Earth's surface, so displacement will become 2r, because we'll be going from r to 2r, it's travelled r, is this particular expression. Okay, I now know I've got this velocity squared equation. I'm trying to get time into this. Remember, capital V, this makes life very easy, we're assuming is the square root of 2gr. So I substitute that in for v squared, I get a much neater little equation there. So little v squared is 2gr squared on r. I want to find a link between displacement and time, because I'm going to say velocity is dr dt. So I'll find the square root. I'm going to take the positive square root to satisfy my conditions, because remember we're travelling with a positive velocity and we're saying it never returns. So velocity will never be negative. So I know it's the positive square root for this equation. Okay, so velocity is dr dt. Turn it upside down, so I've got something I can integrate to get an expression. So it's now with respect to r. But g and capital R squared and 2, they're all constants. So I'm taking that out of the front of the integral. All I'm really integrating then is the square root of r. Remember those limits? I said I was going from capital R to 2r. Because we're travelling from r, Earth's surface, up to a height of r above the Earth's surface. So that would be 2r from the centre. Add 1 to the power over the power. Let's sub in. Well, if I sub 2r, remember r to the power of 3 on 2 is r root r. So that's what I'm thinking here. So when I sub 2r in, I'll get 2r root 2r. Sub r in, I'll get r root r. So I'm getting close to what they want. I've also then cancelled the root 2 into the 2, and I've got root 2 on the top. 3 I've brought across. I've factorised out r root r. And so if I factorise out r root r, I'm left with 2 root 2 minus 1. And so if I multiply that with our root 2, I get 4 minus root 2. I've also cancelled the capital R on the bottom with the capital R there. I'm getting very close now. So if I rewrite it as a third, 4 minus root 2 times root r on g. Is that what we wanted? I do believe it is. Okay. 3 questions. That's all I'm going to get you to do for now. 3 questions from Patel, just to get your head around it, before we introduce this idea of resistive motion and what have you.